Thank you for the kind words, Tamara. And thank you to everyone, friends in Broderick Lab, Cecily and Kyle and Peter, and my friends at MIT at large. I really appreciate you being here today. So I'll talk about one thesis chapter, and at the end, I will mention the connections to the other parts. Markup chain Monte Carlo is commonly used to make data-driven conclusions. However, we might be worried if our major conclusions could change after removing a small amount of data. Our work will provide a fast way to check if this happens. This is a collaboration with my co-first author, Ryan Giordano, collaborator Rachel Meir, and of course, my advisor, Tamara Broderick. So to jump in, we'll look at a motivating example from economics. Researchers such as Angelucci et al. Study microcredit. It's a kind of loan given out to small businesses, particularly small businesses. The hope is that it improves economic outcomes of the population it's deployed to. This study is an influential randomized controlled trial on the impact of microcredit. One question they ask is, do businesses that receive microcredit have a better profit at the end of the study? One may use a Bayesian model and MCMC to analyze this data. Using the posterior mean, you might see that actually microcredit reduces profit. So you could say that it's actually hurtful to the households in this RCT. Well, how useful would this finding be? Not immediately useful if what you're interested in is the impact of microcredit outside of the RCT. So for instance, a policymaker might want to know if, might want to advocate against microcredit outside of Mexico. To do so, they need to know that microcredit remains hurtful outside of the data gathered in Angelucci et al. More broadly, we know of many examples in epidemiology, education, ecology, where people use Bayesian models to analyze their data, and they want to know if their conclusions generalize. If you're interested in generalization, what could you do? One very intuitive idea is checking if your conclusions could change after removing a small amount of data. Our work in particular will show that for this RCT, you could remove just 16 out of over 16,000 observations, so less than 0.1% of data, and make microcredit now appears to help rather than to hurt. In this case, we say that the conclusion depends on a small number of households. We don't know if these data points are going to be present in the world at large, so we worry about generalization. So this was concerning for this analysis, but you're not doing this analysis, you're doing something else. We might be interested in knowing if that analysis is sensitive as well. A natural idea there, how would you actually check if this happens, would be to enumerate over all data subsets of certain size. Unfortunately, there are way too many subsets to search over. Your search will not finish in multiple lifetimes, so this is not enough. So we'll have to turn to approximations. Has this been solved by previous work? Because I'm going to tell you, it's not. Existing approximations, such as Broderick et al., the first work to formulate this kind of sensitivity, only tackle estimating equations or optimization, so not MCMC. So this is where we will come in. So first, before us, there have not been any approximations for dropping data in MCMC. Our first contribution is extending Broderick et al. To MCMC-based conclusions. And then in this extension of ours, we face a problem that was not seen before in dropping data. In particular, our approximation is a random quantity because of the randomness in MCMC. So here we'll provide a quantification of this variability and how it could be used to diagnose sensitivity. Finally, we have experiments on some real data analyses to analyze the quality of our approximation. So to describe for the next 40 minutes, I will follow this outline. First, we'll look at another motivation for dropping data as a generalization check. If you're interested in this check, the natural idea is to do exhaustive search. We'll talk about how expensive and not viable that is. We'll want to turn to approximations after we see the costs. But before we could establish what our approximation is, we'll need some notation. With the notation in place, our approximation will be given in two parts, both of which take very little time to run relative to MCMC. Then finally, I'll show you some experiments with economics and ecology. On a simple model, our approximation works very well. However, on complex models with, say, hierarchical structure or many parameters, the performance is mixed and a lot of room to improve. So in case you need more convincing that dropping data is interesting, here's another reason. So let's put ourselves in the shoes of an economist who wants to make a broadly applicable conclusion. To check for generalization, you might use standard generalization checks like confidence intervals or p-values. For concreteness, let's say your confidence interval for the treatment effect is entirely negative. In this case, you'll say that, oh, on my data that I gathered, there is a negative effect. But also, for the population at large, I think there's going to be a negative effect. So you've made a generalization claim here. The issue with this sort of statement is that we've used confidence intervals to make these statements, but we know the confidence intervals don't make strong assumptions that real data does not satisfy. In particular, they assume that data is an IID sample, but realistically, we know that real data is not exactly IID. So like the data from the households in Mexico is not the same statistically as the data from the Philippines, say. So what you can now hope for, you settle for, is that real data deviates from IID-ness by only by a small amount. Small enough that your assessment of generalization is still correct and your major conclusions still hold. How might you verify this hope? Again, we're going to bring up checking under deviations. So for instance, if you could produce some small deviations from IID-ness and change your conclusions, then you would worry about small deviations as a whole and worry about generalization. A very common kind of deviation we see all the time in practice is that a small fraction, say alpha, of the data could be missing. This may be surveyors that try to give people the treatment just could not reach a fraction alpha of the population. If we could change our conclusions by dropping this fraction alpha, we might be worried about generalization, since it's a kind of small deviation. We're not worried about, say, removing alpha equals 10% of data. That's a lot of data, and we expect changes. However, what ultimately constitutes small alpha is subjective, like a p-value threshold. We will be working with the default alpha equals to 1% here. So hopefully that convinced you that dropping data is interesting. The natural thing to do, as I've said, is to do brute force. We'll next talk about how not viable that is. So in a nutshell, and as Tamara already mentioned, there's going to be a combinatorial explosion in this idea. Let's say you're worried about removing 0.1% of the data. The RCT data has about 16,000 observations. Dropping every 0.1% of data already means enumerating over 10 to the 54 things. A truly mind-boggling number. Even if each MCMC run takes only 1 minute, which is already very expedient for MCMC, this exhaustive search will still take more than 10 to the 48 years. So yeah, I'm here snickering. I think everyone gets the absurdity of it. So we'll have to turn to approximation. And the problem here we've kind of funneled in is there have been existing works on dropping data, and they face a similar exhaustive search, but they apply only to estimating equations or optimization-based conclusions and not MCMC. So this is where we will come in. Before I could tell you how we approximate things, I'll need to introduce some notation. I'll do it in two parts. First, I'll introduce regular Bayesian data analysis, and then I'll extend the notation to dropping data. And my running example will be microcredit, both because it is simple and because later on we experiment. So we'll have capital N observations, and shaky. In microcredit, there is an indicator variable for whether or not the household receives microcredit, and there's going to be a profit measured at the end of the study. An econometrician might analyze this data with a Bayesian model. For instance, they might model profit as a Gaussian random variable. There's going to be a baseline mean of profit, mu. If the household is in the treatment arm, the treatment effect theta is added to the baseline mu. The value that we see is a noisy realization of this mean, and the noise is governed by this sigma. We're going to try to learn parameters mu, theta, and sigma from our data, and I'm going to denote the vector parameters by this beta. I'm going to use the notation Ln to denote the log likelihood of the nth data point. An econometrician might have some some expertise on the problems you're studying, and they might use this prior P of beta to encode domain information. The two of them combined give us the posterior. Its density at beta is equal to the product between the prior and the n likelihoods. Pretty standard stuff. Practically, though, we don't use the whole posterior. We use summaries of the posterior to make conclusions. One kind of summary, we'll call these summaries a quantity of interest, and we'll denote them by phi. So, for instance, in linear regression, it's very common to focus on like a regression parameter, a regression coefficient, say beta d, and then look at the sign of its posterior mean. Or an econometrician might say that a treatment is impact was helpful if the majority of the posterior mass for that coefficient lies on the positive half line. In other words, we could be comparing the lower endpoint of an uncertain interval with 0. So those are kind of two, and perhaps more, quantities of interest. Computationally, we're not able to evaluate the quantity of interest in closed form because of difficulty in there's no closed form expectation in general. So it's very common to use Markov chain Monte Carlo to estimate the posterior, and I'm going to be using this notation beta superscript here. For instance, you may approximate the posterior mean with the sample mean of your sample, and you'll use this sample mean to make conclusions, for instance. So that's regular Bayesian data analysis. To drop data, we'll need to indicate how the quantity of interest is a function. It depends on the observations included in the data set. So we'll use notation of data weights to do that. These are a collection of n values, and I'm going to collect them in a vector W. Each vector W defines a weighted posterior. So its prior is still P of beta before, but now in the log likelihood, we multiply with Wn. If you set one of these Wn's to 0, it means you drop the nth observation. You recover the regular posterior by setting all the weights to 1. Quantity of interest is no longer phi, but now it's going to be phi of W. And for instance, you should read this as the mean of your regression coefficient under the weighted posterior. So with this notation, we'll be able to cast small data sensitivity as a constraint optimization problem. So without loss of generality, I'm going to assume that your decision threshold is 0, and originally your quantity of interest is negative. So the constraint in this optimization is that your weights are binary. Each data weight is binary, but also the number of zeros allowed in this vector does not exceed n times alpha. And this constraint is reflective of us not dropping more than fraction alpha of the data. So hypothetically, if we solve the constraint optimization problem and we see that the optimal value is positive, we know that there is some dropped data that changes the conclusions, and so we'd be worried about generalization. So what we're going to try to solve is this optimization problem, solve/approximately solve the optimization problem. Yeah, so, and I brought up this point a few times. The finding the maximum using brute force is just not an option. Now we'll start talking about approximations. On this slide, I will provide a fast approximation of the worst case posterior mean. I'll make a note that our method could also apply to the other types of quantities of interest, but for now, just for keeping it simple. This is the maximization problem again. Mathematically, it's convenient to subtract the original quantity of interest, 5, 1. This doesn't change how we do the maximization, and we could recover the maximum value very easily. Yeah, so we know from past works that do data dropping approximations, although they don't apply to MCMC. For instance, the original work used a linear approximation to avoid the exhaustive search. While we're not working with estimating equations anymore, this is still a very relevant idea to our work. And in particular, we're going to replace the posterior mean with a Taylor series. So in this display, the left-hand side is the change in the posterior mean. The right-hand side is first-order Taylor series of the left-hand side. Usually, we mostly care about data weights that are a binary value, but here we are caring about the behavior in the continuum 0, 1. We've expanded the Taylor series around weight W equals to 1 here. If you look at this linear approximation, the only term that is non-trivial to compute are the partial derivatives. Like, what are these? We can't rely on Broderick et al. Anymore because we don't have estimating equations. However, we could tap into well-known results that derivatives of the posterior expectation are actually covariances. And what I mean by that is this kind of relationship. So the left-hand side is the partial derivative of the posterior mean with respect to the nth data weight. The right-hand side is the covariance between the regression parameter and the log likelihood of the nth data weight. And here, we're taking expectation with respect to the regular posterior. So this relationship has been shown before in the literature, although it has not been used to detect small data sensitivity in the way that we're doing right now. One example of use of it has been quickly characterizing the frequentist variability of the Bayesian procedure, for instance. And this is one of Ryan's paper. Okay, so now coming back to what we want to do. We've reduced the problem to computing posterior covariances. That is still in itself not solved because expectations are not available in closed form. So we'll have to estimate them. If you recall from previous slide, we've been using MCMC to estimate expectations. So here we're going to reuse those very same samples to estimate these covariances. So my estimate is going to be denoted hat of psi n. It is in English just the sample covariance between my parameter and the nth log likelihood. And this notation is a bit of a shorthand, but you should read it as the evaluation of the nth log likelihood at the MCMC sample. Okay, so we have our sample covariances. this gives us a way to estimate the linear approximation from here with the sample, with the estimates. And this is just replacing all instances of the partial derivative with the corresponding sample covariance. Then we'll optimize this right-hand side. So to see how to optimize it, we'll first rewrite the objective slightly. So in this right-hand side, in this form, it's clearer that removing an observation contributes negative hat of psi n to the objective, and the contribution of different data points are additive of each other. So to solve this, we propose to sort the sample covariances, and we'll remove the most extreme values. So that's our approximation of what the maximum value should be. In addition, we also have an estimate of what the maximizer itself is, and this is just the indices of the most extreme sample covariances. So yeah, this has been our underapproximation. It remains to show you that it is fast. So we have both a bound on the time complexity it takes, and also a lot of numerical evidence that this is much faster than MCMC in the first place. So typically, so in modern implementations of MCMC, such as the STAM programming language, not only do we have the samples, beta, but we also have the log likelihood evaluated at all of the observations. So then we only need to compute the sample covariances and then sort them. The time to do it is not more than n times s plus n log n. Practically, our approximation takes very little time to run compared to MCMC. One case, MCMC took 12 hours, but our approximation took only 2 minutes. So again, much faster than 10 to the 48 years.
Can I ask a quick question?
Yes.
So there are 3 levels of approximation going on, correct? So there's the Taylor series approximation.
Yeah.
Then there's the approximation you use for the covariance.
Yeah.
And then there's I guess this algorithm that approximates the maximum, because you don't compute that exactly. Is that
This should be exact. So
okay.
so
the algorithm is exactly solving the max.
Yeah.
Okay. So there's only 2.
there's only 2.
There's only 2. Okay.
Yeah.
Okay.
Yeah, exactly. Ashia. So first approximation, this squiggly line is this function with its Taylor series.
Mhm.
And then second approximation is the partial derivatives with the sample covariances. But like the final approximation is this one.
Yeah.
And then we
Right.
can solve this exactly.
Exactly. Okay.
Yes,
I just have a question about in the line, like we know from past works.
passwords. This one?
Yeah, about the like covariance being equal to the derivative.
Yeah.
So the first argument of that covariance in general is just gonna depend on like whatever parameters phi is a function of in general. So if I were interested in like the sum of beta 1 and beta 2.
Exactly.
Okay, got it.
Yeah.
And what if I'm interested in like a quantile of beta instead of an expectation? Does the covariance change? The derivative, yeah.
I don't know what the covariance for the posterior quantile is,
Okay.
and I have that as one of the next steps questions.
Okay, got it. But this is a special form just for the expectation.
This is really expected.
Got it.
Or, by extension and chain rule, any smooth functional of
Right,
the
yeah.
posterior expectation.
Yeah, got it.
So somehow maybe you could. So yeah, like I definitely want to talk about quantiles later, but currently I don't know how to do it.
Okay.
There might be ways to do it. There should be ways.
Yeah, nothing comes to mind immediately.
Nothing comes to mind immediately, so yeah. Yeah, great question. Cool. Yeah. So this is one. So this is an approximation of the worst case theory. It is analogous to previous approximations that people have come up with, but for estimating equations or optimization. However, we have to deal with a sort of error that has not been seen before in estimating equations or optimization, and that's Monte Carlo noise. So we had to make an additional approximation. We had to approximate the partial derivatives with samples, and that is a noisy process just because of MCMC randomness. So in this section, we'll talk about a way to quantify the variability in our approximation that is due to MCMC randomness. And for instance, not variability due to, say, like sampling variability of the data. So to do this, it's first helpful to conceptualize what we're doing as applying a deterministic function to a random sample. So I'm going to use the notation delta hat to describe this function. In general, the MCMC has temporal dependence. It's not actually independence draw. But to discuss motivation, I'll start with a simpler case where IID sampling is possible. And for instance, this is conjugate models. In the IID case, you might use the bootstrap to quantify variability. Very brief review. First, we will resample with replacement from the empirical distribution. I'm going to denote the resample draws by beta star. Then we'll evaluate our estimator, delta hat, on this resample draws and use one of its interquantile range as our confidence. So now stepping back to the general case with actual time series dependence, we expect this sort of idea to actually underperform. And for the reason why, we'll make some figures. So on the left here, I'm plotting a trace plot of a give sample. What we want to understand is the behavior of this sort of plot across different MCMC seed. But already from this kind of plot, we could see there's like temporal correlation. There are many periods in which the time series consecutively decrease or increase. For instance, one episode is this one in purple here. Can the bootstrap tell you, like give you a proxy for this? Answer is no. On this plot here, for each time step, I am drawing a value at random from the set of values visited by the give sampler on the left. Because it ignores all sort of time information. This sample looks like white noise and does not have any episode of increase or decrease. So to better handle time series dependence, we'll use what's called the block bootstrap. Let's see some figures. It will help explain what we're doing. So first, I'm just replicating the trace plot from above. In the block bootstrap, I first splice the time series into a number of blocks. I'm going to label the blocks from 1 through 4. To generate a resample, first I'm going to draw blocks at random. Then I'm going to concatenate them from start to end and have that as my new time series. For example, this is what it might look like. This is the result of concatenating block 1 with 4 with 1 with 3. So visually, you could see there are again periods of consecutive increases or decreases, and the sample looks quite similar to the original sample. This kind of resampling scheme has one parameter, the block length. In this case, it is 250. We would like both the block length and the resulting number of blocks to be large. Longer block lengths lets you capture longer temporal dependence, but having a lot of blocks gives you kind of roughly more IID things to do estimation with. But because the product between the two has to be equal to your sample size S, there's going to be a trade-off. Our work will not use such a long block length. We actually use a very small one, relatively small, like L equals to 10. Okay, so that's completes our description of the approximation. And then for the rest of the talk, I'll show its performance on some real data analyses. So for the first one, I'll be applying it to analyze the RCT data that we saw. Our approximation is fast, and it also gives a very accurate assessment of sensitivity. I will explain it in 3 parts. First, I'll give some context. Then I'll run MCMC. And finally, will assess sensitivity. So for context, we're considering a variant of Meagher's microcredit analyses. So Meagher 2019 analyzed the same data we're going to be analyzing, but with ordinary least squares. Meagher 2022 is an example analysis that use Bayesian models and MCMC to estimate the impact of microcredit. Our variant takes elements from both, and we designed it to make the point that even a very simple Bayesian analysis could be sensitive to small removals. The last point of context I'll mention is that our paper will also has sensitivity analysis of the more complicated microcredit analysis. So let's jump in to the analysis itself. We've already seen the log likelihood and the data when we're setting up notation. Just to recall, we're going to be most interested in theta, the treatment effect. We complete the log likelihood with wide student t prior, and we'll estimate the effect with MCMC. Running MCMC took 3 minutes. On the right, I'm giving a histogram of the treatment effect draws and some key sample summaries. So the solid blue line is the sample mean, about -4.5. In addition, I'm plotting posterior mean plus or minus 2 posterior standard deviations. Those are the blue dotted lines. And the interval is roughly -16 to 7. So looking at this, you might come to the conclusion that, well, the posterior mean is negative. However, my uncertainty interval contains 0. So I'm not conclusive about microcredit hurting or helping. Now, we'll ask, can you change these conclusions by removing a small amount of data? It takes only 2 seconds to apply our approximation. I'm going to be plotting our confidence interval for the worst case quantity of interest after removing data. Apart from the confidence interval, we also propose which data to draw. We're going to remove set data, rerun MCMC, and actually plot the quantity of interest. The punchline there is our prediction range usually contains the refit value. So for the first sensitivity question, we asked, is it possible to change the sign of the posterior mean? Things are a bit rotated right now, but the posterior mean is in blue. We want to know if the posterior mean could be positive. To be confident, we actually asked, can the entire confidence interval be positive? The first time this happens is by removing 0.1% of data, and I'm going to mark it with this purple arrow here. We could remove the data we proposed and rerun MCMC. Doing this, we see that the X marker at that value of percentage is actually positive. So we say that our refitting confirms our prediction. One point I forgot to mention was on the x-axis here, that's alpha expressed as percentage. If we're considering a grid of alpha values here, the largest being 1%. Each refit here takes roughly the same time it took MCMC, so about 3 minutes. So that's one sensitivity question. The next one we'll look at is changing Bayesian significance. So before explaining this plot, I'll quickly jump back to the histogram. Currently, the uncertainty interval contains 0. But hypothetically, if you remove data and the right endpoint moves to the left of 0, then the uncertainty interval does not contain 0, and you'd be able to make some significant conclusions. This is what we're trying to do with this middle panel. Originally, the quantity of interest is positive, and we want to find the first confidence interval that is entirely negative. The first time it happens is after removing 0.36 of the data, this alignment here. Removing set data and checking the quantity of interest, we say that the refit actually confirms the prediction because the X marker is indeed negative. Finally, we'll try to generate a significant result of the opposite sign. So we ask, is it possible that somehow microcredit has a positive and significant effect? Coming back to the histogram, if somehow you could remove data and move this left endpoint to the right of 0, then you would have changed the sign and the significance of the conclusion. Returning to this bottom panel, unfortunately, we're not able to predict if such a change is possible. The reason being, even at the most extreme removal amount, 1%, our confidence interval still contains both positive and negative values. So we're not sure. In this case, we recommend you increase the number of Markov chain Monte Carlo runs. Go ahead, Jenny.
Oh, sorry, I was just wondering if each of these bars were created from like actual refitting or was it from approximation?
The bars is from the approximation. So the bar comes from resampling the estimator under the block bootstrap resampling distribution. So the time it took to make one of these bars is 2 seconds.
Oh.
Under 2 minutes. Is that helpful? Should I go back to the slide or?
Yeah.
That's okay. Cool. Yeah. So those are, I'd say, pretty good results for albeit a simple model. Next demonstration. Oh yeah.
I just had a quick question about the block bootstrap.
Sure.
So I was just trying to get an intuition for what would happen. So obviously you have those nice plots that show like sort of the bootstrap paths if you assume independence. But in terms of like an over or under estimate of the quantity that you care about,
Yeah.
Is it generally true that for data that are correlated in time, if you take the standard bootstrap, you're gonna overestimate uncertainty? Or is there, yeah, is that right?
If you usually your time series has positive correlation,
Right.
Under that case, the bootstrap underestimate sampling variance of the sample mean.
Yes.
Because like say, bootstrap will, like long answer is like the sample mean, this asymptotic variance needs to incorporate information at different lags. Whereas, and the information at different lags is more than the information at lag 0 because of the positive correlation. The bootstrap itself just knows about lag 0. Yeah.
Right.
Yeah.
Makes sense.
We can talk again about later too.
No, that makes sense. Yeah, I just want to
Like,
thanks.
okay, so let's move on to the next demonstration. Here we're gonna switch. We're gonna move away from economics and we're gonna look at a study from ecology, or particularly tree death.
Can I ask
Yes.
a quick, would it make sense to take alpha to be actually much larger? If all these assessments are giving you kind of this grid all the way up till alpha, so you're
Yeah.
able to discern at what point does this
Yeah.
kind of parameter estimation change?
Yeah.
Part of the reason why for both you were not able to understand exactly when this takes place is
Yeah.
because you said alpha equal to 1.
Yeah.
So if I were kind of going to use this,
Yeah.
wouldn't I take alpha equal to like 5 and then
Try to
just-
see the breakdown.
exactly, like, oh, might not be 1, but it might be 1.3.
Yeah.
And at that point, that's still maybe intolerable.
Yeah. So I think
It would take much longer, I'm assuming, or does that, what's,
really what we could do is like we could support like take if you want to say well not even if you could like update these, like these don't take long. Like
Okay.
if you give us an alpha that you care about, then we could tell you.
okay,
And like basically because of the sort. Once you do one sort, you know the order for everyone.
right.
So-
right. So it could easily
It's
accommodate.
amortizing.
I see, all right, gotcha.
But I think one point we would say is at some point you have to make an assessment of
Like at what point you're cutting things off.
yeah, at what point is like alpha too
Yeah.
large? Like well, here again, 1% is a subjective assessment. Somebody could have come in and said 0.5% is already pretty large.
Mhm.
I will say, if you're interested in that sort of what is the smallest breakdown point, like the actual AMIP paper, talked some about that,
Mhm.
and
But since yours is amortized, as you described, you could actually just ask that kind of question seamlessly from
yeah,
this
Yeah.
analysis. Like,
Yeah.
okay,
maybe in like a binary search kind of way, you start somewhere, start at the other end, try to find. It's not gonna be as clean
Right.
as the AMIP paper,
Mhm.
partly because of this noise in the confidence interval. It makes a lot of things difficult for us, but I think somehow you could do a binary search.
Mhm.
Haven't fully figured out the detail, but
thank you.
um. Cool. Yeah, next demonstration, tree mortality. Our approximation is still gonna be fast. That hasn't changed, but it's not gonna look as good as on the simple model. So for this demo, we'll also talk about context. We'll then run MCMC, and then we'll assess sensitivity. For context, these are European scientists, tree scientists, who wants to understand the association between the amount of available water in some sort of ecosystem and the amount of excess tree mortality in that region. We're interested in that for conservation reasons, for management, etc. These authors were very acutely aware of generalization. They were very motivated to expand upon previously small and local studies in hopes of making a broad scale assessment. However, what our work today will show is that even if you have generalization in mind and you design a big expansive study, you might still be sensitive to removing small data. So you haven't fully solved that problem. So that's enough context. For the model itself, it's too complicated. I'm not going to tell you all the nitty-gritty details. The highlight today will just be that the linear predictor based on water balance that tries to predict tree depth involves many parameters. There is an affine population relationship between water balance and tree depth. But on top of these population relationship, there's also many regional affine relationships. The authors tessellate Europe into roughly 3,000 regions. So each region receiving at least 2 parameters, resulting in at least 6,000 regional parameters. They model things hierarchically. This is a very common application of Bayesian thinking to share strength. And MCMC is very commonly used to fit these types of models. So running MCMC is 12 hours, which in some sense is a lot more typical of the time you expect to spend on MCMC. This is the histogram of the slope parameter theta along the MCMC sample. The posterior mean is about -2. The uncertainty interval is roughly between is roughly from -3 to -1. So looking at this, you might say that water balance has a negative and significant association with tree depth. Now, again, we'll apply our method to ask, can you change the conclusions after removing a small amount of data? It took only 2 minutes to run our sensitivity framework, much faster than 12 hours. Although here, our prediction is usually more extreme than we could realize by refitting. For first, we'll try to change the sign of the posterior mean. Originally, it's negative in blue. The first time that our confidence interval is positive happens at removing 0.17% of the data. And I'm going to mark it again with the purple arrow. We can remove the data we propose and rerun MCMC. Takes 12 hours again. However, in this case, the X marker is a bit bunched up, but the X marker has not broken the 0 threshold. So this refit does not confirm our prediction. Looking at the rest of the X markers, though, we'll see that the first one that is actually positive is at 0.22, and it's in cyan. So I'm going to mark it with another arrow here. Okay, so second sensitivity question we ask is again changing Bayesian significance. Quantity of interest here is the right endpoint of the uncertainty interval. If we could move it to positive, we will change the significance. The first time this happens is by removing 0.1% of data, and I'm marking it again in purple. And this time, I think we got lucky. The change actually does happen if you remove and refit. The X marker is actually positive. But looking at it might be a function of how we discretize the percentage grid. It could be like for a smaller value of alpha, the change would have happened too. But also looking at the flare between our estimate and the actual refit here could be quite large. Finally, we asked, is it possible to change the association between water and tree depth to be actually positive and significant? Our method predicts that this is possible after removing 0.17% of the data, and it's going to be again marked in purple. However, that X marker after refit does not break 0. The first time an X marker lies above 0 is actually at removing 1% of the data. And still, we remark that we kind of make pretty extreme change, whereas not able to realize nearly as much. So we've seen in our approximation work pretty well in a simple model, but not so well in a complex model. The next 2 slides will be dedicated to understanding why. So while we expect and we hope an analyst run the tests that we showed in the previous 2 slides of like plotting the confidence interval and perhaps refitting the data, refitting after removal, we don't expect an analyst to run the following tests because they're more computationally expensive.
Small question
Yes.
about the removal. So when it was actually 1%, so you have to actually remove more, is the set you have to remove overlapping with the set you're identifying, at least with this method?
So the set, we only, well, from one run of MCMC, we only propose one set.
Right.
Yeah.
So it could just be that with 5 additional points or, X number of additional points.
Yeah.
I'm just wondering, was that set part of the core set you would have actually had to remove?
Oh, like how good is it
How good
actually?
is it
Like the worst
actually?
case.
Yes.
It's a great question. I don't, I'd say we know how to estimate that worst case set
Mhm.
better if we had more MCMC draws.
Right.
But from just one MCMC draw,
It's
we
hard.
already kind of understand it's quite a noisy process.
Right.
We'll try to explain the noise a bit later too, but yeah, currently we don't think, we're not too, we have reservations about saying that this is like a great estimate of the maximizer set. We know that it's a useful construct sometimes, but yeah, it's hard to diagnose with just one MCMC draw how good you are, for sure. Yeah. Yeah, so so the next 2 slides will be more diagnostics. We've seen some shortcomings of our methods on real data, and we're going to try to unpack what are the possible reasons that it could have manifest this behavior. So one natural candidate to worry about is MCMC randomness. Like in optimization, you run things, might get unlucky with a bad seed. Something like that could have happened. You could have just got unlucky. So we'll need to check or need to account for MCMC randomness somehow. Secondly, while we focus on comparing our confidence interval with the refit after proposed data, ultimately you care about how the confidence interval contains the worst case refit. Yeah, like you're asking. So in an ideal world, we could formulate this as checking how often under MCMC randomness the confidence interval contains the worst case quantity of interest. Since we make a linear approximation of the quantity of interest, natural way to break down this question is actually with 2 checks. So first, how often does the confidence interval contain the result of the linear approximation? And then separately, is the linear approximation good? For this slide, I'll just talk about the results for the first one. If you're interested in the second check, check out our paper. So before giving you the results, let's quickly talk about the experimental setup. So by result of linear approximation, I mean the sum of the most extreme partial derivatives. So if you recall, for posterior expectations, the partial derivatives are equal to the covariances. And here, I'm summing across an index set I that already sorts by the most extreme partial derivatives. The frequency with which a confidence interval contains some ground truth is usually called the coverage. And we're going to use another level of Monte Carlo to estimate this coverage. So this is partly why this is a very expensive check. We run 900 more markup chains. Could be done in parallel, but still takes quite a while. Doing this has 2 benefits. So first, we could average our estimate of the sample covariance across separate chains. And this will give us a high quality estimate of the ground truth. Separately, on each markup chain, you could construct the confidence interval and evaluate whether or not the interval contains the ground truth. This gives you 960 indicator variables. If you take the mean of those variables, it gives you a high quality estimate of coverage. So that's the setup. I'm going to show you results for the simple model now. We'll see that confidence interval contains the ground truth with very good frequency for the simple model. And in this figure, each panel corresponds to a quantity of interest. There's a red dashed line. That is the nominal coverage level, 95%. So we hope that our confidence interval contains the ground truth at least 95% of the time under MCMC randomness. The solid line is the sample average of the 960 indicator variables. The error bars are confidence interval for the actual coverage, just based on binomial tests. So you notice here that the point here is that the estimated coverage is very close to the nominal level. You want 95, I could give you 93. And error bars are quite small, so we're pretty confident. Fortunately, in the complex model, we see a case where the confidence interval can have very poor coverage of ground truth. Before jumping into the figure, I'll make a note that the figures I'm going to show was actually generated by first subsampling the original large data set. So theoretically, it would have taken thousands of hours. Maybe I should have asked Tahid for Amazon credits, but I didn't. So I did not have the budget to do it. I settled for subsampling 2,000 observations. Hopefully, this is a representative check. We see here there are two trends, one much more alarming than the other. So first, as percentage goes up, our coverage usually decays. However, the more alarming trend is that for changing significance, we are grossly wrong about where the ground truth is, using our confidence interval. We want to be right 95% of the time. The confidence interval tells us that we are not right more than 25% of the time. So something is amiss here. Okay, so again, another piece of the puzzle that we'll try to break down and understand. Why was it so poor in the complex model? So to do this, we'll first have to actually recall how we computed the interval in the first place. So we first, resampled in blocks from the original markup chain. And then we evaluated our estimator delta hat on the resample draws. Let's unpack what we were doing with delta hat since it's been a while. Calculating delta hat involved computing many sample means, sample covariances, and then a sorting step. So in this notation, I'm just saying this is the order statistics of the sample covariances. Delta hat by construction is the negative of the sum of either ends of extremes. If you want a maximum, then you take the most. You first compute the most negative ones. So of the steps involved in the confidence interval, the sorting part is a non-smooth operation. In the sense that the maximum between a real value x and 0 is a continuous but not a differentiable function. A similar statement could be said about this sorting of like n things. And to add to that, we are not aware of bootstrap theory, bootstrap guarantees in the non-smooth case. For instance, we know that bootstrap gives very good uncertainty quantification in the case of like smooth estimators, like sample means, sample covariances by themselves. So all of this sleuthing just to formulate a suspicion that it is this sorting step that is creating complex dependencies and messing up our confidence intervals. To test this, we could try to remove the sorting step altogether from delta hat. So we'll consider a version of delta hat that does not involve any sorting. So this index set I here is fixed a priori before running any MCMC. For each MCMC, we'll still estimate the sample covariances, and then we'll take the sum of these sample covariances. But here, we do not involve any sorting in the construction of the sum. Well, how do we use this to diagnose? Well, first, we'll construct confidence interval, again by resampling this so-called fixed index estimator. The ground truth that we know should cover is just sum of the partial derivative, just because this is a roughly asymptotically normal version distributed around that. If the confidence interval covers the ground truth well, then we could attribute the issue that we saw on the previous slide is because of the sorting step involved in delta hat. And again, we'll estimate the coverage by another expensive but conceptually clear experimental running like 916 work objects. So the coverage for this fixed indices estimator is given in this panel. Red is again the nominal 95%. We see again a slight decay in the coverage. However, even at worst case, we want 95, we get 91. So for convenience, I'm replicating the coverage plot from the previous slide. Again, note how vastly different the vertical axes are between these two sets of panels. Things are at around 90 here, but here is from 0 to 1. And so the contrast between the two figures lead us to conclude that the severe underperformance was due to sorting. What might you do with this kind of understanding? Well, there's always more to understand. Like, for instance, why is it so bad for changing significance, but kind of fine for generating a significant result of the opposite sign? I suspect that something has to do with how well we are approximating posterior standard deviation. So it was not shown, but sig and both usually take the form of posterior mean plus or minus a constant of the standard deviation. We know how well our approximation is doing for the posterior mean just by looking at the sign panel, but neither of these are like give a clear indication of what happens for just the posterior standard deviation. So I think that would be the first next step. We encourage you to also look at these other questions. One question Eric already brought up very excellently is, can you extend this framework to posterior quantile? It is a very common kind of quantity of interest, but currently our framework could only handle posterior expectations or posterior standard deviation. Secondly, we think it will be better to set a problem-dependent log length rather than the default 10. If you just look at the simpler problem of capturing the uncertainty of, say, like the sample covariance, like each individual hat psi n, that is a function of the parameter, the log likelihood, and the product between the two. If your MCMC chain has temporal dependence longer than lag 10, then we expect correct setting of L equals 10 to be could be better than that. And then finally, I like to understand what is actually the cause of difficulty in the complex model. Our example has two kind of competing explanations. It has both a lot of parameters, 6,000 of them at least, but also they are organized and coupled together hierarchically. So it would be nice to tease out which is which. And to do so, you might start with, say, just a high dimensional problem like linear regression without a conjugate product. So, separate out hierarchy. So let's summarize what we talked about today. We developed and tested a fast approximation for the removal of the worst case small data in MCMC for Bayesian analysis. Our approximation is much faster to run than MCMC in the first place. However, the performance in simple models is good, while the performance in complex model leaves room for improvement. We'll archive this work super soon, so please stay in tune. Yeah, so today's been about supervised learning. My thesis, and actually how I got to this sort of problem, is actually about unsupervised learning, as Tamara mentioned. I see the work today as a necessary first step towards like the analogous problems in unsupervised learning. And in theory, there's nothing to stop applying these sort of approximations to the models you see in unsupervised learning. So for the next few minutes, I'll mention the other chapters in my thesis. we know of many data analyses that take the form of estimating some sort of latent traits in a population. So you might want to know, I'm a Wikipedia buff, that's how you could test. You might want to know what are of the million documents of Wikipedia, what are like the major themes, and like, which documents manifest those themes. To encode structural information about this sort of data, you could use Bayesian probabilistic model. My thesis identifies and solve a number of computational issues associated with Bayesian unsupervised learning. So for one, there are existing works that aim to speed up Bayes through parallelism. However, I could show that they struggle to the so-called label switching problem in unsupervised learning. Where I come in is I use a representation to evade this problem. And when multiple parallel processors are available, I can derive fast and accurate estimates of Bayes posterior. If you're interested, please take a look at this paper. And second problem I tackled was Bayesian nonparametrics. These are flexible models that could that posit a countable infinity of latent traits in a population. So for any finite data set, there's always more to learn. However, computers cannot actually learn a countable infinity of things. Generalizing past works and providing more guidance, I derive accurate and easy to use linear finite approximations. If you're interested, please take a look at this paper that's under advanced publication. Yeah, these are just references in case anybody wants to follow up. Yeah, thank you.